Well, Louisa, it's been a pleasure getting to know you today, and it was also a pleasure to read your book. And in reading your book, one of the first things that I asked myself is, what sparked the idea to write a book on the history of the concept of quantum entanglement? So please tell us.
Well, I was lucky enough when I was little that my dad was learning quantum mechanics for fun, and he would tell me these wonderful things. So I was just a 6-year-old, and he would say, electrons act like they can be in 2 places at the same time, and this chairs, mostly empty space. And so I had this idea that physics was where the magic was. And then I took a lot of physics courses that were somewhat less than magical, some of them. And I actually dropped out of the physics major, which I'm embarrassed to report in front of many people who, but I wasn't, anyway, I became an English, I was sort of halfway through.
Where was this at?
Oh, at Dartmouth. And so halfway through, I was like, okay, I'm not good at this. I'll do something I'm good at. And I became an English major. And then I started missing physics a lot, which is always a good experience. And I took a philosophy of science course. And the professor gave us a paper by David Merman called Quantum Mysteries for Anyone. Actually, 2 papers by him on the same subject, which was the subject that I would devote the next decade of my life to. And it was just, I was so excited. So this paper was describing entanglement. It was like, this is what I wanted to be learning about. Why were my professors not telling me about this? I've taken a year of quantum mechanics and we didn't talk about it once, because this was before the year 2000, which is a big watershed year, and people didn't talk about it. And but the physics department let me do an independent study, and this book ultimately grew out of that independent study. So it was,
wow.
Yeah, it was a fun experience.
It gives me hope for teaching courses in philosophy of science. Maybe I'll have a student
You can
who goes
make
and writes a book.
such a difference.
Yes,
Exactly.
yeah.
I don't think I've even thanked her.
I do like to hear that. Now, in the beginning of your book, you quote, I love this quote from Heisenberg. Physics rests on, or science rests on experiments, but science is rooted in conversations. And of course, you describe your book as a book of conversations. And this was a great stylistic choice for your book. It's turned out to be really successful. What inspired you to make it a book of conversations?
Well, I didn't start that way, because why would you? But I was struggling with how to tell this story, and it felt so much that it's not understandable why things happen the way they did without knowing the people involved. And it would have unfolded in a different way with different people. And in fact, it's almost, I haven't ever really explicitly done this in a talk, but there is a kind of metaphorical level that relates to quantum mechanics, in that the relationships are as important as the states of the individuals, and that people are what they believe. It's all in relationship, and these physicists are, that all these conversations, even as I was doing this independent study, I was with a wonderful professor named Miles Blanco, who he was teaching me the nuts and bolts, and we were both reading about the history, and just having all these amazing, all these characters are so interesting. I still, to this day, feel so moved by how interesting these people were and what they cared about and how much they disagreed and how they fought and how they also got along. And it was just all related to, and every time I would read somebody writing a kind of description of the history, this history for the general reader, it just felt all the air had, because they weren't allowed, because what I did, nobody should do, you shouldn't do this, because it's essentially creative nonfiction, and I, but it sucks that why did it happen this way? Why did people? And Heisenberg was my ally, bless him, because he wrote his memoir, Physics and Beyond, which is really fun. It's all conversations. And he's like, I don't know if I remember them right or not, but this is the way it happened. And he kind of gave legitimacy to the idea that, and also another, in a different way, George Gamow, whose lovely book, 30 Years That Shook Physics, I bet that some of you know it, and he has this kind of goofy approach of teaching a little physics and then telling a story about how the day that Niels Bohr was a good rock climber, and one day he and probably Gamow and Lev Landau or something were walking down the street of Copenhagen, and Bohr decided to show a rock climbing move, and he climbed up the bank. There was a Danish bank there, and Bohr gets the second story before the police come, but Bohr's so famous, he's a god in Denmark, so it was fine, and the policeman was excited to meet Bohr. But stories like that, I love, and of course that's not particularly relevant to the Bohr atom or anything, but it gives a sense of what Copenhagen was like, and why the Bohr Institute would have been such a lovely, incredible place for so many people, and so things like that also, and Gamow also, as I did little drawings and portraits, so I just copied Gamow. Anyway, yeah.
Were there any particular difficulties in reconstructing these kinds of conversations? And
so
did you take any liberties?
Did for the people that haven't read the book, so I really, there are conversations in the book between the great quantum physicists, and in the later period, it's all people I interviewed and conversations that I witnessed, but in the earlier period, I am taking people's letters and memoirs and biographies and saying, Bohr said this, and we know that, for example, lots of times the memoirs or letters or whatever they might be will say, there's this lovely story of Einstein coming to visit Bohr in Copenhagen and them being so involved in conversation that they kept missing their stop they're on the tram and they keep missing their stop, and so you can kind of, so what I was doing was saying, well, what were they talking about? And there's all this material, and as I was reading the material, they're such single-minded people, and at the beginning, the fraternity, not many women, of quantum mechanics was a very small group, and they were all having the same conversation. They all knew each other, and so in a way, I took great liberties, and embarrassingly, when I was writing, I now work in a bookstore where the first step when a book comes in, you say, is it fiction or nonfiction? And that's the, so this is superposition. And I didn't know, it's so stupid because I was a reader, but I think this happens to, I watch people come into the bookstore and they're like, I don't understand the layout. And I say, this is fiction, this is nonfiction. But at the time I didn't know that the book would have to go through that gate. And so I wrote it pretty blissfully. I mean, knowing that I wanted to absolutely only have people say things that they said, and so in that sense,
so it is fairly faithful to the kinds of things.
As faithful as I could make it, but it certainly isn't. I wasn't there. I'm quoting letters. Sometimes the letters are from a year later, or it's not accurate, of course, on some level. On another level, I completely stand behind it because they they were talking all the time. This is what they were doing. And these were the subjects they were talking about. These are their words. And yes, it's probably not right, but I think it's not fair to all of us to just pretend that they weren't human and that they weren't, that it was just sitting in a room writing an equation or something, receiving it from above. Yeah. So, but it has sort of hobbled me for writing another book because I no longer am brave enough to do that again now that I know. Enough, right? Yeah, right, exactly. It's naive. It's total naivete. Yeah, yeah.
Well, that's great. So we should talk a little bit about quantum entanglement. So in your own words, what is quantum entanglement? Especially, how does it defy our classical expectations, right? There's something strange about this. Yeah. How would you describe quantum entanglement?
It's so lovely that this is part of the way the world works, and that when you think about what the matter that we're built out, the same matter that we're built out of, and the air we breathe, and everything, any quantum object that interacts with another quantum object, if they don't interact with something else, doesn't matter how far apart they get, they are described by a single equation. They are, in some sense, acting as if they're one thing, and they can be across the universe from each other. And it acts like, you touch this one, and the other one acts as if it's responding. And that is just so counterintuitive and fascinating. And so there's the level of this is part of the way the world works, and it's not really understood even by the people who've studied it for years and years what's really going on a level that those of us who are English majors would like to understand. What's going on? And there's also the level that how science works, which is interesting to me, that how much is the more you learn, how much it opens up more mysteries. So
yeah, and in many ways your book is a whole study in how science works. I mean, it's about quantum entanglement, but it's also about scientists and how they invent new theories, and very interesting. And of course, the physicists that you describe in your book, there were a lot of perplexing things about quantum mechanics that we don't have time to talk about, like wave-particle dualities, the nature of spin, matter waves. Can you visualize these things? What about measurement? And given these probabilities, they were arguing about, does this violate causality, like determinism? But so we're keeping focused, everybody, on entanglement. But there are a whole lot of other conversations we could be having that are included in your book. So read the book, and you can enjoy those conversations. Getting to entanglement some more, though, Einstein is one of the people who had a primary role in helping to at least shine a spotlight on this feature of quantum mechanics. What was Einstein's role, and in particular, can you say something about this paper that everybody calls EPR?
So one thing that was really fascinating about learning this story is realizing how early on Einstein was noticing that there's something about the quantum theory that it feels like we can't treat things as a thing all by itself. And this is a problem because this is how we do science. We split things, we find out what's this thing, and we cut things into smaller pieces. And this ability to separate one thing out and treat it as if it's not going to be affected by other things is really hard to imagine how you do science without that. And Einstein, starting in 1909, so basically he had, in 1900, Planck sort of starts quantum theory, sort of walking backwards into it. And then in 1905, Einstein says light is quantized. So the quantum theory had just started, and Einstein was already trying to say to people, there's something funny going on. And he his arguments with Bohr that spanned decades of the quantum theory were Einstein kind of sharpening what's the nub of this problem. And he would talk about, he had a Gedanken experiment, which is a thought experiment that he kept presenting to Bohr and to as he went around essentially of a box of light, and the light that it leaves it being entangled with the box. And though those words weren't, and Einstein saw this problem of non-separability of that you can't. It ultimately sort of comes down to, well, he's like, this is the end of quantum mechanics. There's something wrong with it. It's not, you can't do this. This is not science. There's something majorly, something is rotten here. And
so he was looking for a more.
Yeah, he was like, I proved it wrong, basically, and later. Someone who's involved much later in this story, John Clauser, described to me how, if you think about Einstein's career and starting with thinking about relativity and how you can't talk about time and distance without talking about clocks and meter sticks. There's these things that we think, that you're answering the question of when and where, but in this very kind of practical way. And this argument that he was making against the quantum theory was ultimately asking a question, how do we answer the question what? We've got these fundamental questions. What is time? You measure, it's what you measure with a clock. What is distance? Well, it's what you measure with a stick. And what is what? And the EPR paper was what brought this entanglement situation to the physical review, and
EPR stands for?
And so EPR stands for Einstein, Podolsky, and Rosen. He was working with two younger colleagues, and in the course of who essentially did the work, it was Einstein's thing that he would go around talking about, but he was never going to publish it. And these two younger colleagues sort of got interested and started hammering out a paper. And during the course of researching this book, I had an amazing conversation, which can't be verified, but it's quite amusing that Podolsky, one of these guys, told his colleague, well, we really added Einstein's name without asking. Who knows if it's true? But Einstein clearly wasn't very involved. He was deeply, passionately involved in the subject and involved in the thought experiment in a general way. But the way it came out is a very non-Einstein-y way. So it was sort of, but be that as it may, the paper actually triggered Schrödinger, who had written the equation, who had had the insight. The Schrödinger equation is one of the sort of foundational descriptors, the way quantum mechanics talks about the world, and the entanglement is implicit in that, but Schrödinger had only sort of kind of noticed it, and other people really hadn't. So Einstein's saying, spooky action at a distance, this box can't affect this light photon 500 million miles away, alerted Schrödinger, wait, this is what's happening in my equation, and that started this discussion between Einstein and Schrödinger because of what's going on here, and Schrödinger did christen this mysterious connection as entanglement in English, which we all has certain connotations that are sort of messy, and then Verschränkung in German, which you go to Germany and everybody goes like, I'm like, what does it mean to you? And they go like this. It's like a rigid cross-linking. So it's two very different words to describe this mysterious thing. But anyway, Schrödinger wrote a series of papers inspired by this EPR paper, kind of exploring the territory that entanglement, which he...
In one of these, a cat comes up.
Exactly, and in one of these, a cat comes up. And so and probably many of you know this story, but in these letters, Einstein says to Schrödinger, he's sort of making fun of Schrödinger because Schrödinger wanted to believe that his equation could be the whole thing, and that you wouldn't need any any big object to measure something and to make it make sense. Schrödinger wanted his equation to describe it all, and that the world could all be waves. And Einstein said, well, you know, of course this is ludicrous, because what if you had gunpowder that would be triggered by the decay of a radioactive decay? So very quickly, it might take the radioactive decay a long time to happen, but the gunpowder's either gone off or it hasn't, and so very quickly the quantum mechanical description of the gunpowder would be exploded plus non-exploded, but we all would hear the bang, we'd know, and this became Schrödinger's famous cat, where he describes the cat either being poisoned or not being poisoned as a result of a quantum event, but nobody believes the cat is both, well, actually, probably there are people, I should take that back, but between Einstein and Schrödinger, well, obviously, the cat is alive or dead. The cat can observe himself. The cat knows that he's alive or he's dead, even if we haven't opened the box. And so quantum mechanics needs somebody to open the box. The opening of the box is sort of a metaphor for
for making a measurement,
yeah,
or taking an observation,
yeah,
which seems to be funny for the theory, right?
Why should
that matter?
Why should that matter?
To
yeah,
what the state of the cat is,
right?
So,
yeah.
Yeah. Now, Einstein and Schrödinger were sort of in a minority at that time. So there's this other. The standard view of quantum mechanics at that time was the Copenhagen interpretation, and associated with names like Bohr, Heisenberg, and Pauli. But as you say in your book, that viewpoint seemed to stifle investigations into entanglement. So it was really Einstein and Schrödinger, the minority view, that made a difference here. How did the Copenhagen interpretation stifle that kind of discussion?
It's a good question, and it in a way it's something that people are still looking into, but Bohr would just use these words that were pretty vague, and it just happened, and it's a tricky situation because Bohr was a person who made such great contributions both to physics itself and to raising up generations of physicists. So he had this wonderful effect, and yet in this one area, the way he talked about it, what he was interested in, he just had sort of a blind spot to this. And he had the privilege, you could say, of arguing with Einstein endlessly on this, and so in part of it is sort of an interesting look into how different people just see different problems in the world and care about different aspects of them, and Einstein just couldn't get through why this is mysterious, or why you might wonder whether this is really happening. And Bohr must have been more clear as a speaker, though people do describe G.P. Thompson, who's a British physicist, describes Bohr's speech as wrapped in the gingerbread of his helplessly amiable way of talking, and how Bohr would use these long sentences with all these dependent clauses that were often, as G.P. Thompson described, unduly flattering to his listener to believe that you'd even thought of that. He's trying to answer all your questions, and so it seemed. So anyway, as in person, people had a hard time understanding him, and he would mumble and writing on the blackboard. There's a great story about Bohr writing. He's giving a speech. He wants to talk about. He's talking about harmony, and he writes harmony on the blackboard, and his handwriting is so messy that when he describes, he thinks, actually what I mean to say there is complementarity, which was sort of his favorite. So he just dots. He puts a dot in the middle of the word. Harmony becomes complementarity. So as a writer of words that get printed, Bohr is very hard to understand. And so all these, and somewhere in all of that, this is not true of Heisenberg and Pauli, who are much clearer, but there was something about that, that fog that worked well for some things and really totally obscured entanglement. And there's this fascinating, to me, maybe not to, but sociological thing of, well, Einstein and Schrödinger are both loners who just work by themselves and more or less, or with one student or a mathematician or something. And Bohr is this intensely social person who creates a school around him. And so next generation, what happens, the Copenhagen interpretation becomes shut up and calculate, which Bohr would never say, but still that's how it gets. By the time you get a couple generations away, you've got this situation that when you reach and
this is the context in which we find someone like John Bell in the 1960s working sort of on the sidelines, kind of keeping it hidden from people. That he's thinking about these issues about quantum entanglement, quantum non-locality, hidden variable theories. And so he again, kind of hidden from everybody else, he works on this issue. Can you tell us a little bit more about what John Bell was?
Bell is sort of the hero of my book and the hero of this story generally. He was an Irish physicist working at CERN in Geneva at the big particle accelerator, and he literally did not tell his colleagues that he was interested in this subject at all. And but he described himself working under his desk at night. Basically, it was his hobby, and what he saw is that so in the era of Einstein and Bohr arguing, this is the teens through the 30s, and then you've got World War II and everything changes, and Bell is at CERN in the 60s, but in fact he wrote his crucial paper he finished it in Madison, so just couple hours east of us here, so that's sort of fun. I had forgotten that. This paper in which he showed that this discussion, which everybody had thought was a metaphysical one that you could kind of leave to Einstein and Bohr and to people who liked philosophy, and Bell showed that it, and there's a great quote of Pauli, who was just a wonderful, funny person. I mean, I think probably maybe a little less funny to be close to him because he was so witty, and he would, but he described how Einstein is always talking about things that are on the order of how many angels can sit on the head of a pin. It's just there's no answer, and what Bell showed is that this is Einstein's. It's not a metaphysical question on some level. Bell looked at the situation that had been described in this EPR paper, where in the EPR paper they Einstein, Podolsky, and Rosen describe entanglement with two particles interacting and then separating, and their position and momentum are entangled. And then what Bell was looking at a similar situation and showing that if you look at that there are certain ways when you measure the two particles, you can always predict if what one does, the other does the exact same thing or the exact opposite thing, depending on what kind of particle they are. And so if you measure a lot of this situation and you see they're doing exactly the same thing no matter how far apart they get, and and Bell used to talk about this in terms of twins. When you can meet twins and who even twins who are separated at birth. In the 80s, there were a lot of there were these twins who were discovered who had been separated at birth, both named James, and they both married. I forget the whole sequence, but it's just a bizarre sequence of coincidences, and it actually led to a founding a study for twin studies here. And Bell used to talk about that as a metaphor for these particles are behaving like identical twins, even more so, because what this one does, you know what's happening, and but what Bell showed was that nobody was thinking about, because nobody was interested in the subject, nobody was thinking about, well, what if you measure slightly different aspects of these two particles, and not just the times where they give the same answer, you know they're going to give the same answer, but slightly different things. You can build up a statistical picture, and it's just amazing when you dig into it that obvious everybody. The twin hypothesis that there's genes, that these particles know something. The reason that when you separate them and you measure this one and you know things about this one is because there's something about them that's there that you're measuring, just like...
And you say it in your book, I mean, you talk about shared DNA in the case of twins, right? And so
Bell showed that if you look at different aspects, if you compare if you add up the other things you can learn about these particles, it just absolutely contradicts. There's no way the particles can have DNA. There's no way they can have anything inside of them that already knows. And who can explain the twin-like behavior? And Bell kept, so there was that paper that he published in Madison, and that was 1964, and that's on the Einstein-Podolsky-Rosen paradox, and that's the crucial paper. But he kept trying to explain because nobody would listen, and people weren't interested. And the paper that and he's a beautiful writer, I should say. In a way, this book is following the physicists who are beautiful writers. I completely, and he's trying to get the attention of his colleagues. And he, in the 80s, he wrote a paper called On Bertelsmann's Socks and the Nature of Reality, which doesn't mean anything to anyone, except Bertelsmann, who was his colleague, who would always...
And someone you met.
And who was a physicist at the University of Vienna, in Vienna now. And Bell noticed, but never told Bertelsmann, that he noticed every day Bertelsmann comes in, he's wearing... His socks never match. And for 3 years, they worked together at CERN, and Bell never mentioned the socks, but he was noticing. And when Bertelsmann went back to Vienna, he was swiftly followed by this paper. And I used to be able to quote the beginning by heart, and I'm just going to see if I can do it, because it's so lovely. So Bell says, "The philosopher on the street who has not suffered a course in quantum mechanics is quite unimpressed by these Einstein-Podolsky-Rosen correlations. He can point to many similar examples in everyday life. The case of Bertelsmann's socks is often cited." Dr. Bertelsmann likes to wear two different socks of two different colors, and which color he will have on a given foot on a given day is quite unpredictable. But when you see that the first sock is pink, you may be already certain that the second sock is not pink. And Bell does this little drawing of Bertelsmann with his beret and his beard striding in the door, and you just see one leg, and there's a little arrow saying pink sock, and then another arrow, not pink. You can't see. And this was still the 80s. It still took a long time for the crucial people. There's a thin chain of people that cared, but it took. And
so in many ways, this Bell result in the 1960s seemed to make this philosophical question an experimental one.
Exactly.
And this got people excited. Well, a few people excited maybe doing an experiment. Can you say a little bit, because you talked to some of these people like Clauser and Shimoni and stuff. Can you say a little bit about how that kind of came out, the experimental work that these people started to do? But again, there was a sociology in physics at that time where this was not the cool thing to be doing.
It really wasn't, and it was a real struggle, which of course makes a more fun story. And at every turn, the people that are trying to do these experiments and show, let's see this amazing effect. Maybe it's not real. Maybe quantum mechanics is wrong. John Clauser, one of the guys that did the first experiment, he believed he was going to prove quantum mechanics wrong, which would be he wrote Bell to tell him about that he wanted to do this experiment. It was the first time Bell, this was in 69 or 68, I guess, and Bell later said that was the first time he felt that anybody was interested, and he wrote back saying, you know, of course it's going to come out the quantum mechanical way. Of course, there's a very small chance that you'll disprove quantum mechanics and then you'll shake the world. And Clauser knew, he knew what it was totally, he was going to bring down quantum mechanics. And but everywhere around him, there were. Yeah, it was just a subject that nobody wanted to fund. Nobody wanted people to do it, and it's why it's just so. And these early researchers, even Alain Aspect, who's the French guy, the drawing out with the Hercule Poirot mustache. So he did his experiment. So Clauser and Friedman do this experiment in Berkeley. They publish in 1972, I think, and they've demonstrated that entanglement at least persists in their experiment over a machine that's probably from a little bit beyond you to a little bit beyond me, which is far for photons of light, which is what they were.
Did they show you pictures of the experiment?
Yeah. And so I did a drawing that was based on the photographs that and apparently the machine is still there somewhere, but I didn't get to see it, but then in the 80s, a bigger experiment in France done by Alain Aspect, and things were slightly changing, but still Aspect tells this wonderful story of going to Bell and saying, I'm going to do this experiment, and Bell's first question wasn't anything about how he was going to do the experiment, or he said, do you have a permanent position? So,
yeah, that's a... and so that leads us to, I mean, who were the first people then? So we talked about Einstein. Einstein thought that there was a problem with quantum mechanics, and that's how he sort of started shining a light on entanglement, because he thought that hinted at some kind of problem. But eventually people started to view this as a resource. And can you say a little bit about the first people to begin to see that this might have practical uses?
So after all this sociological then the kind of, well, Richard Feynman does say, because of entanglement, quantum computers, which Chad is going to talk about, are going to be able to do things that no classical computer can do. So that's 1981. Feynman is saying, this might be useful, and you'd think with somebody towering like Feynman, but still, you know, it took. But there's this lovely story of David Deutsch, another. He also saw this. He's another pioneer of quantum computation, and he. But the story that who also kind of saw this, but people weren't really listening, and this lovely story of Arthur Eckert, who was a postdoc with Deutsch, and he was in the library reading the EPR paper for the first time, and he, just as a hobby, was into codes. And so he's reading this paper with a background that nobody else who'd read the paper had, and he read this whole situation as an eavesdropping situation, as a way, they're talking about, can you make an unbreakable code? And Eckert publishing a paper on using entanglement to make a quantum key distribution, a way to, that was kind of the chink opening the door of
quantum cryptography.
Are you telling me this can be practical? Is what Bell said, and then things start happening, and
when was that?
That was 1991. Okay. Then 93, Seth Lloyd shows how to do, probably pretty soon. But Chad will be better placed to describe this. But it's just so exciting, the change that happens with these few people saying, this isn't a problem, this is an opportunity. Wow, nobody had thought about all these quantum mechanics and is all about, well, you can't say that, no, you can't do that, no, Heisenberg uncertainty, no, you can't. And to look at all these things and say, this is an opportunity to do something that nobody can do. And that kind of change starts happening in this century is when suddenly it becomes, with, again, only, there's still not a lot of people, but to view it as an opportunity, as a magical moment.
Okay. Thank you, Louisa. This is a fun discussion. First, you'll be around afterwards to talk and sign books.
Thank you.
So why don't we start? Just tell us a little about the paternity leave.
Oh, wow. So officially, for the record, it's my first month back after paternity leave,
Okay,
which was
good.
extensive and wonderful. And it's just been a wonderful experience. It's our first child, and we're both having literally the time of our lives. It's just so much fun.
And you told me previously your daughter has an interesting name. Maybe just tell them a little bit about that.
Oh, yeah. So, well, her name is Seymour Grace Rigetti, and she's named after at least 2 giants of computing. And I'll let the crowd kind of figure out who those might be.
Do you have a Minnesota connection, or at least a Chippewa Falls, Wisconsin connection? You can kind of figure out the first name.
Yeah.
So tell me a little bit about how Louisa's book, you read it in 2009?
Yeah. So, is this? Can you guys hear? Okay. No. This okay? Okay. So I'll just speak up
Should
then.
he
Yeah.
hold this one?
Yeah. Maybe I'll hold that one as
Or
well.
another one?
Yeah. Okay. So, I remember very vividly, actually. I did a PhD at Yale from 2001 till about 2009. I'd taken some kind of time away from physics to work in a startup. I knew I wanted to get some experience outside of academia. But I'd come back to Yale to kind of wrap up my research and then continue to do a postdoc. And I remember walking down Chapel Street one night and kind of popping into Atticus Bookshop. And I saw Louisa's book, and it was The Age of Entanglement. And I thought, well, there's no there's no books about entanglement. This doesn't make what's this? What's this amazing book? I have to get this. So I bought the book and immediately fell in love with it, and it was just it's just a wonderful and book that brings these characters so alive and so vivid and so real, and all the stories are things that Pauli and Heisenberg and Schrödinger and Einstein and all these people. If you're a physics major, you hear about them continuously, but you know nothing about them.
Yeah.
You literally know nothing about their lives. And it's just so magical to me to be able to spend some time with those people who were really the giants of physics and the giants of the quantum theory that had worked so hard to formulate it all. And I just think, for me at that time, it kind of, everyone who's done a PhD or will do a PhD, it's a grind. And it takes a lot of energy and a lot of time. And at that point, it really just kind of rekindled my love of physics and reminded me of all the reasons I'd become a physics major in the first place, kind of 10 years before.
That's beautiful. Well, that's a real testament to your book, Louisa. I mean, we have one of the pioneers of quantum computing whose career is reinvigorated by the book. So one of the things that I would love to put some pressure on Louisa on is to do an addendum to the book. To do a couple chapters bringing us up to date. And if she did that, I think we should have a chapter on how a kid from Moose Jaw, Saskatchewan, founds a quantum computer company. Can you tell us a little bit about that journey?
Yeah, I grew up on a farm in Saskatchewan, Canada, close to Moose Jaw. And I went to college in a town about 60 miles away. And I remember being a junior physics major. And I was taking quantum mechanics, and I was taking computer science courses because they were required. And I was not doing well at either. And I also remember being just incredibly frustrated because I could not understand quantum mechanics and what it really meant and what it was really all about. And I also just couldn't understand computers and how does a computer actually work? Okay, not about how to turn it on and start writing some things in BASIC or Python today or something like that. how does a computer actually represent and store information? And I've always, I like to work hard, but I like to work hard on things that are kind of a synthesized view of, to make sure that we're spending my time in the right ways. And so I decided that I just kind of join these two things together. If I could understand both quantum mechanics and computer science and how computers actually worked, and around the same time, this was 1999, around 2000. This group at IBM Research had actually, built a quantum computer using nuclear magnetic resonance technology, and they'd run some basic algorithms on it. And I thought, wow, so I can just study quantum computing and then solve both these problems, and or not solve both these problems, but and to treat, scratch my itch to really deeply understand these two things and just work on that one problem. So I ended up looking around for places where I could work on quantum computing, but I didn't want to do the theory. I wanted to actually build them. I've always just wanted to build things and kind of make them real in the world. And I think that my passion is really to make things very boring. Ultimately, I want to take things that are very, very complex and find ways to make them simple and eventually boring, just kind of automatic for the world, and for myself, really. And so I wanted to build quantum computers somehow, and I looked around, and there was a professor at Yale named Michel Devereux, who's an incredible man, an incredible human being. And I decided that I wanted to work for Michel. And so I applied to Yale. I managed to get in, and I went without visiting or without having any acknowledgement that Michel would accept me into his group. But he was the only person I wanted to work for. Ended up spending 7 years there with him. I remember walking into Michel's office one day, my very first fall at Yale, and in his way, he was proposing a topic for a thesis to me, and he said, well, we've managed to build the single qubit, but the problem now is really to generate entanglement. And I thought, well, what, and I asked him, but what is entanglement? And he said, oh, that's a good question. And so for me, it just was the start of what ended up being a kind of 8-9 year conversation about, through work, through physics, and just conversation about really what is quantum entanglement and how can you generate it or produce it kind of in a controllable manner. And ultimately, that is kind of the crux of quantum computing and why it's interesting and why it's so hard.
It's interesting because the time period that you were at Yale directly coincides with when Louisa was working on this book, almost exactly the 2 dates. So her book kind of starts to wrap up in the 2000 to 2004 timeframe. Can you talk about what was going on with your group at Yale? What were these huge breakthroughs that you and other schools were doing that really brought that entanglement forward in terms of quantum computing?
Yeah, well, maybe I should use a couple of slides. First of all, I was a student studying with these great people and was learning all I could from them. And so great. So
can everybody see that, by the way?
There is, at a really high level, with quantum computers, this is technology is going to be fundamentally more powerful, more efficient, and just it's harnessing a more fundamental understanding of nature than what today's computers use. And there's a long history dating back thousands of years of humans basically building tools to store and process information using their most recent and up-to-date understanding of the way the universe works. And quantum computing to me is just a part of this thousands of years long story of human history interwoven with our technology and our information technology, really. And it's been, as we learned from the book, it's been 100 years since the foundations of quantum theory have really been formulated. It's time. And so, but what has happened really, the 2000s were, the 2000s were really about coherence, okay? So the first decade of the 21st century was really about learning how to build deterministically and reproducibly or manipulate or control or operate in a particular way systems that would display and behave this quantum mechanical behavior over a sufficient duration of time, the quantum coherence time, that you could envision doing computations with them, okay? And that's quantum coherence. So it was really kind of the main thrust of the first 10 years of the 21st century. And on the left here is something that is, has become kind of known as Sholkoff's law, after Rob Sholkoff, a professor at Yale. And effectively what we've seen is that in superconducting qubits, which is one of the kind of predominant technologies that is being pursued for large-scale quantum computing, the coherence times have increased by about a factor of 10 every 3 years or so, and that dates back to about 1999. So we're talking...
So this is kind of the equivalent of Moore's law in the classical...
Well, people want it to be that, but it's really more of a steady rate of progress by physicists chipping away in the lab. This is not kind of a Moore's law. It was kind of more of an economic incentive that drove a real commercial technology. This is all kind of pre-commercialization, but just about our own ability to understand and formulate the right frameworks by which to progressively and continuously improve the quantum coherence time. And ultimately what that is just finding ways to more judiciously and carefully isolate a quantum system from its environment while also still maintaining control over it. And this is the crux of quantum computing. So we've seen about a 10 million x increase in the quantum coherence time over the past 15 years. And that was the 2000s. And then kind of the 2010s, like the most recent decade, has all been about 2-qubit gates or deterministically and reliably generating specific entangled states with a very high fidelity or very low error rate within kind of 2-qubit systems. And now at Rigetti Computing and some other companies and some other labs around the world, we're all kind of at the point where people know how to do these 2-qubit gates, if you will, with between 1% and 5% error per gate. And that's getting close to good enough. Getting up to around 99% fidelity is good enough where you can then start to really envision doing large-scale algorithms and large-scale calculations. So, and that's really been the thrust of the past 10 years is 2-qubit gates and high-fidelity entanglement. And now, like going forward where we're at is there's two key things, and the next 10 years of the field is really all about this. It's integration and algorithms. Okay, so integration going from not from 1 qubit to 2 and then 10, but from kind of tens to hundreds of qubits and then thousands of qubits, enough where you can really embed and represent interesting problems on that machine. And then on the algorithm side to really figure out how to program and make use of this quantum computing resource. So traditional classical computers have been around for a long time, dating back to mechanical systems. I like to think of an abacus as one of the a really simple kind of mechanical computer, and the algorithms that we use and the frameworks and the abstractions that we have for programming classical machines are really old and established and are the accumulation of thousands of human lifetimes of effort. And quantum computing is in its infancy. And everyone knows about Moore's law for chips, but there's also an effective kind of Moore's law for classical algorithms. So if you control for a fixed classical computing capability, our ability to take advantage of that to solve the same kind of problem is getting exponentially better over time. And so we're at the start of this era where quantum algorithms is going to start to undergo this kind of exponential increase in the power of different systems. And so the big challenges going forward are really integration of the next 10 years and quantum algorithms.
Okay. Let's step back a second, because one of the things that I found when I looked through various presentations that Rigetti your staff had done, was it was the first time I really understood what people were doing. I don't know why your team makes it so clear. So walk through with us the approach that you guys are taking to quantum computing, and kind of in particular talk a little bit about Forest and whatnot. Yeah.
So I believe that there's a real value in clear communication around this technology, simply because it is such a hard to understand area of science and engineering. And so we've really worked hard to, and we in the whole field have a long way to go, but we've really worked hard to try to present things in a clear manner. So we are what we call a full stack quantum computing company. What that means to us is that we engage in the full gamut of activities that are needed to build true quantum computers and to do useful things with them for customers, for users. We're not a research organization. We're not a physics shop. We really view ourselves as quantum engineers, and we're building technology that's useful with the intent of being useful and solving real important problems. So that means that we actually we've built our own semiconductor style fab, so we design and manufacture our own chips. We integrate those chips into kind of a cryogenic, ultra-low noise environment, and we operate them with a control system that we also develop through custom hardware. And ultimately, then we have a kind of software and infrastructure for delivering access to these machines over the cloud. And so people can control them and program them remotely and can use them as a sandbox to kind of begin developing quantum algorithms. Mm-hmm. And the approach that we take so this is actually kind of the core of our platform and of our stack. This is a 19-qubit quantum chip. This kind of gold-plated puck that you see is about 3 inches in diameter, and the chip itself is about 1 inch by 1 inch. And underneath the cap, or underneath the lid on the chip, is a layout of 20 superconducting qubits. So the qubits themselves are based on superconducting thin films, and these qubits are effectively, well, I think there's a slide on this actually. I'll come back to it. Okay. The qubits are these kind of concentric rings you see on the right-hand picture, and the qubits are effectively little resonators that resonate at a certain frequency. And these devices represent quantum information by storing individual photons of energy at that resonant frequency at which they will ring if you hit them with a microwave pulse. And so ultimately what you can do is to apply sequences of pulses to each of those qubits to manipulate their state between having 0 or 1 photons in each qubit, or a superposition of 0 or 1 photon in each qubit. And then you can also apply a different flavor of microwave pulses to the devices and kind of add in the amount of energy that would be required to make up the difference between 2 of the different frequencies on the qubits. And ultimately what the qubits can do then is 2 of them can conspire jointly to absorb a single photon or not, or to emit a single photon. And you don't know where it came from, and or you don't know where it went. It's jointly stored in both qubits at the same time, and that is the essence of generating quantum entanglement on a chip like that, where the information about the location of the photon is completely lost, but you know it is there. And that's kind of the essence of the spin up versus spin down of in an EPR experiment or something like that. And but ultimately, as I said, our goal is to kind of to make this really boring. And so what we've done is build a software stack on top of this that treats all those things just as kind of Boolean quantum logic operations that you do on some register, some quantum memory, because that's what computer scientists and algorithm researchers need. That's the level of abstraction they need to really do their work, which is to develop ways of taking advantage of this kind of computing capability. Yeah, and then so let me talk a little bit about Forest. So Forest is ultimately our, is kind of the platform that and the development environment, the software development environment that we offer to our customers and users. And it's really the kind of hub in the ecosystem where all this really fascinating and beautiful physics just comes together in kind of a living, breathing ecosystem of algorithms researchers and chemists and machine learning people to kind of develop and take advantage of this quantum computing capability.
I mean, it almost seems like the approach you've taken, everything that's gone on ahead of you in the cloud is really ushering in the ability to now do quantum computing in some ways.
It's been really important, for sure. And the most critical element of that is that we can build a machine and operate it from our labs in Berkeley, California. We're based in the Bay Area. And people can program it from all over the world or all over, wherever we're offering service. And kind of on that point, last weekend, last Friday and Saturday, we hosted the first ever quantum hackathon. And we had teams from, I think, 10 or 8 different countries from around the world. We had a team from Japan, we had teams from Europe. We had a group of high school kids from Toronto who were 10th graders participate in the quantum hackathon. And my goodness, it was the most inspiring couple days of my life. It was so amazing to see the amount of engagement and how the app and the capacity of people to really do amazing things with this was really just beautiful to see. Yeah, so one of the reasons that's possible is because they're learning about it remotely. They're learning about it over the cloud, but then bringing everyone together into the same space is also just creates a bunch of energy, and it's a really fun environment as well.
So the approach that, I want to go back to the hardware, on the approach that you've taken on the quantum processors, talk a little bit about the approach you've taken versus the other quantum computing companies.
Sure. So there's there's different ways to build quantum computers, and but they can kind of be thought of in two broad ranges. One is where you come at it from the top, and the other is when you come at it from the bottom. And first of all, let's start with the bottom. Okay, so you can take something that is intrinsically a quantum mechanical, device, system, or state. Things like this are, the spin of an electron, or the spin of a nucleus, or a single electron, or something like that, or an atom, or an ion. You can take those things now, and they have these amazing properties, and typically they have they're really isolated from the environment because their electromagnetic cross sections are extremely tiny, right? So a single atom doesn't interact very strongly with the world around it just because it's so tiny. But that makes it challenging to manipulate. They're hard to put them exactly where you want them, and they're hard to kind of couple together. And that's one approach. And there's ion trap technology. There's photonics where they use individual photons as the qubits.
And they don't scale very well.
Well, all of them have different trade-offs. Is the right way to is how I would describe it. Now, the other direction is the one that we've taken, and the one that was really the reason why I wanted to go work at Yale with Michel Devray, was because what they were proposing at that time was, well, let's not start from an atom and try to build a qubit. Let's start from something we know how to build and turn it into a qubit. And the things that we know how to build are kind of semiconductor style silicon chips. And the amount of kind of cumulative investment that has gone into that kind of technology over the years is in the trillions. We have really deep mastery over the materials properties and things like that of silicon chips from the computer industry. And so well, let's make chips that can be easily, and if we can learn how to make qubits lithographically like we make transistors through traditional or methods derived from traditional manufacturing techniques, then we'll be able to scale that technology significantly because, lithography, you can build 1 million for the same cost of building one. Right. And so that was the approach that the kind of Yale team drove. And the key differentiation difference relative to transistor-based chips is that we're using superconducting materials rather than semiconducting materials. And superconducting materials like aluminum can support the flow of electricity with no loss, with no dissipation, or with no heat generated. And that's a core element of being able to support these long coherence times. Now, the things that are elsewhere going on in the field, so I'll go to here. There's a lot of, over the past kind of 5 years, things have really ramped up. The IBM research has a significant effort. I was a part of this for a while after I went from Yale to IBM and then started Rigetti Computing. And they use a similar superconducting approach. Google now has a really significant effort. They're also using the superconducting approach. Okay. Microsoft Research has invested, made a significant investment in seeking to build these machines as well. And they use a combination of kind of superconducting qubits with some more advanced particles that we're not yet sure that they exist, but we strongly suspect they do, but they're really hard to kind of demonstrate in nature, called non-abelian anyons. And then
even named that after a gentleman, an Italian, who's actually disappeared, right?
Yes, the Majorana fermion. Yeah. Yes, it's an amazing story which we won't get into, but I'll leave that for Louisa's next book maybe. And then Intel, of course, is getting involved, and the way I see this is that this is going forward. Computers are going to all be quantum classical hybrid computers. There's going to be a quantum part to all high-performing computers. And computing as an industry is going to have, we're not going to get rid of traditional computers, but there's just going to be this new capability that is kind of really directly leveraging the properties of quantum mechanics to store and process information in more efficient ways. And we're just in the early era of that industry, and things are really just now getting rolling. And there's also a handful of startups that are kind of participating in the ecosystem as well.
I think one thing that I noticed in looking through various materials is that you folks are very forthright in terms of being, I'll say, realistic in terms of problems that quantum computing will solve or won't solve. Talk a little bit about where you see first applications for quantum computing.
Yeah, so first and foremost, quantum computers, as I mentioned, are not going to replace traditional computers. They're going to augment them, okay? And our view of the world is that, this kind of quantum classical hybrid computing approach is what's going to lead to the most significant near-term and likely long-term applications as well. And what you do in that, the reason for that is because it's very hard to build these machines. And they today are really quite noisy. It doesn't mean they're not interesting and useful, but they have a lot of noise. And so there's ways you can develop algorithms to use these machines even in the current era, in their current performance, but where the systems and the results you get are resilient against individual bit flip errors or errors in individual qubits in the algorithm. And ultimately what you do is kind of use the quantum computer to guide the directionality of some optimization loop that is running on some complementary classical computing system. And you use them in conjunction like this. And so Forest in our software stack is really designed to be a quantum classical programming environment for this style of computing. Now, the kinds of problems that you're going to use this for in the near term tend to be optimization style problems. And that's not obscure. That's most of and all of machine learning, frankly, and all of AI research. And a lot of optimization problems. There's just a lot of problems that don't lend themselves to a formulated exact best known solution approach, where you kind of want something that is a good, where you optimize towards a good answer. And this is used in a lot of supply chain optimization frameworks or application areas. And then these are the kind of more macro applications. And there's one that is just so natural and direct that everyone's super excited about it, and I think is going to lead to really significant market impact in the next kind of 5 years or so. And that's what we call quantum chemistry. So when you try to use a classical digital computer to simulate the behavior of a quantum mechanical system, that problem gets exponentially hard to simulate as the quantum mechanical system gets larger that you're trying to mimic. But there's things like small molecules or materials that are themselves whose properties derive from their quantum mechanical nature. And if you're trying to simulate, say, the structure of a small molecule to understand its application or its utility as maybe a drug candidate, well, you need to understand the quantum mechanical aspects of that molecule. And in this case, you can basically directly map variables from the object you're simulating to the quantum computer, because it kind of runs natively on a quantum computer. And so this area of quantum chemistry is a really significant application area. This is it's material science, drug development, even nuclear energy is a part of this as well.
And you've introduced a platform for that, as I understand it, or a tool.
So we have active research in this space. We have some really exceptional researchers at the company working on this, and we've built some tools in collaboration with other people like Google and kind of integrations with Forest that allow people to kind of map problems in computational chemistry onto the Forest toolchain and therefore to run them on today's quantum computers.
So my last question, and then we'll turn it over to the formal Q&A. Talk a little bit more about this classical hybrid with quantum and classical. I think you have a slide on this.
Sure. So, well, in the spirit of the evening, people have talked about in some of the other books that have kind of followed in the wake of Age of Entanglement. Seth Lloyd has talked about how the universe is really a big quantum computer, and that there's this information theoretic approach or information theoretic formulation of quantum mechanics that kind of may help to resolve some of the strange behavior that is manifest in other formulations. And ultimately, I think that that's a really interesting direction, and it may well be very helpful. It's certainly the way I see the world. But I actually think the world is not just a big quantum computer. The world is a quantum classical hybrid computer, because it also represents information in classical states, right, that you don't need a quantum mechanical description of. Your clock is a classical computer, and you do not need to go to quantum mechanics to know what time it's going to be, what time the clock is going to be reading off in an hour. It's predictable from classical Newtonian mechanics. And so we've taken the approach that the framework of computing for the future is going to be one that kind of learns this from nature and marries that on the platform using this quantum classical hybridization. And so ultimately, the technical way to describe it is that we have a shared memory model where you have a classical computer, and the outcome of that computation, the outcome manifests through creating a measurement of the quantum system, which necessarily collapses it into a classical state. Right. And so the outcome of a quantum computation is classical information. And that classical information is stored in an area in our machines where it is directly accessible to CPUs or other classical processing nodes. And therefore, these can be tightly coupled and can be, you can kind of trade off resources and capacities between the two in a very low latency manner. And it's just a completely new way to think about what high performance computing is. And so we have, but when you build computers, you need to do a lot of different things. There's got to be an instruction set. There's got to be a programming framework. There's got to be the hardware and all the integration. And so the key point where this really manifests is through our instruction set, which allows you to kind of manipulate classical and quantum information at the same time and on the same footing.
Okay. This question revolves around essentially conventional risk analysis and risk management. And where can a person see themselves going in terms of various types of risk management with the quantum unit augmenting a conventional computer system?
Well, that's an interesting question. I think eventually risk management and kind of, in a broader sense, kind of optimization problems applied to problems of that type, or optimization approaches will be very helpful and fruitful. I can't tell you how soon that's going to happen and when the hardware will actually be able to provide a sort of quantum advantage for those kinds of problems. But intuitively, there's an element of quantum computing that I think is going to be really fruitful for that direction or for those kinds of problems. It's through this notion of sampling. A lot of risk management and kind of computational approaches to this, from my understanding, rely upon really getting a handle on what all the risks are and like a strong sampling of the potentialities that are out there. And especially hard to capture are the ones that are highly correlated. Okay, the ones where it's 4 or 5 events that all make each other successfully more likely, and then that's what leads to a significant meltdown of the financial system or of a particular fund or something like that. It's exactly that the quantum computers are good at. So they're very good and efficient at storing these high order correlations, and that's what entanglement really kind of is when you start extending it out to multiple different, many different qubits. So I don't think there's anything that's going to change that industry in the next couple of years, but long term, I think it is certainly an interesting application area.
So the sharp point of the whole thing is identification and correlation, and for things that right now are kind of dark cloud developments.
Yeah, and it may not be a purely computational challenge today.
Thank you.
So, quick question. Can you say now what you think or what you project potential sales might be for you and the other players in this infant market?
No.
That's a fair answer.
I think that, look, this technology is going. I think we've gone from, when I started the company, it was quantum computing was not I wouldn't really say it was an industry yet. And I think that now it's almost maybe an industry. And I have no doubt that it's going to be a very big and important industry. And the primary risk that I need to manage as the person responsible for running the company is how soon it's going to be a big, important, and valuable industry, and how soon we're going to be able to solve important and valuable problems with our customers. And that's what the game is today. That's what that's what quantum computing needs to do, and that's really the driver behind a lot of our technology strategy and how we built the company today.
Thank you.
What sort of resources do you think you need in terms of like available quantum computing to solve some of these hard problems? Are there, like, what's the sort of critical mass of things like, when you get these many qubits built, because you're building these things, these are slow. I not say slow, but you have to you're turning these out. This is almost industry. What level do you need to before chemical companies are going to say, or drug companies can do these things, or we can solve these problems? Where do you need to be, and how far away do you think you are?
Yeah, so the framework we use for this is something called quantum advantage. And right now, the reality is, no matter what you hear out there and what you hear in the press, quantum computers do exist. We've built some of the most powerful ones in the world, but they're not nearly as powerful as traditional computers yet. Okay, so quantum computers exist, but they're not really doing interesting and new things yet. And the challenge for the whole field is what we call driving towards and pursuing quantum advantage. And quantum advantage necessarily needs to be thought of along the lines of very narrow and specific problem instances that can be solved doing something better using quantum mechanics. And there's different things, there's different aspects of better. It might be that the time to solution is faster. It might be that the overall quality of the solution, if it's an optimization style problem, is higher. It might be that it costs less to run. It might be that it consumes less electricity or less power to arrive to that solution. There's a lot of different elements of quantum advantage. But the one, of course, is most powerful is just like if you can compute things that were not computable before. And that's what quantum will do eventually. But the impact on the other ones should not be disregarded. Now, the order in which in which it makes sense to actually allocate resources to an earnest pursuit of quantum advantage within a particular segment or industry is, we've kind of drawn that out here. So I think the first one that really makes sense is in machine learning and AI. And specifically, we think that problems related to image recognition or computer vision are going to be some of the first interesting problems that quantum computers will be applied to. And then kind of after that is this thing in materials or computational chemistry or quantum chemistry. And we probably need somewhere between like 200 and 1,000 qubits to do that, coherent, highly coherent gate model qubits to do that with quantum advantage. And then, kind of going forward from there, drug development, drugs are pretty large. They tend to be large molecules, or many of them are large molecules, so it requires a larger quantum computer. The thing that's interesting when you really do this analysis is that everyone talks about RSA and Shor's algorithm, which didn't come up in the story, but was this algorithm that was developed in 1995 by a mathematician named Peter Shor. And what he showed was that if you could build a large-scale, truly quantum computer, that you would be able to crack RSA encryption in kind of polynomial time, if you will, which means that it would be crackable in kind of days or hours or months or something like that, rather than millions of years, which it is today with supercomputers. And so that drove a huge amount of the investment and activity in the space for a long time. And the reality is that we track our own rate of progress very closely, and we try to be very quantitative about this. We're between 17 and 25 years away from having something that is even useful to talk about for that problem. And it may take much longer than that. Okay, so that is not really an application today. And then there's other things that go on beyond that are even harder than RSA.
I feel I should just do the, Shor described his, so Shor's algorithm is 1994,
yeah.
And, but a little bit later he described it, he said, if computers that you build are quantum, then spies of all factions will want them. Our codes will all fail, and they'll read our email till we've crypto that's quantum and dantum. 2036.
A question more on the philosophical bent, so for Louisa first, but both of you. How do you measure what?
It's a real problem. But the lovely thing that this sea change that Chad's company represents, and all that when I was talking to Nicolas Chizin, who did these lovely entanglement correlation experiments using the phone lines of the fiber optic phone lines of Geneva, so demonstrating entanglement over miles, and he said, we've just learned so much more in the between 2000 and I was probably talking to him in 2006 or something, and he was like, in these last 6 years, we've learned more about the shape of entanglement and what we're dealing with than in the entire 70 years that preceded, and so that's part of the magic, and even that's what Feynman's interest in quantum computation was. And this will do this, and we'll learn about why the world is like this. And so this project that has practical things in its future, and there's also this magical thing that making things practical means you really, when Chad's saying that his passion is to make things boring, that's the magic of understanding something we didn't understand before in a really rigorous way. So hopefully this work leads to the answer to that question.
My philosophy of quantum, around all this stuff is that true mastery for humans of a particular physical theory is by building computers out of it. And that's not tongue-in-cheek. Like, you have to completely understand all of the predictions, because think of what a computer chip is doing today. It's testing your understanding of it at billions of, at gigahertz rate across billions of transistors in parallel. And ultimately, it's a really great detector of physical flaws in the device. And so you have to have complete mastery of the physical systems that go into actually building those microchips and programming them to really build useful computers. And I think, to me, we will resolve the very fascinating and kind of these fascinating questions around what is entanglement and what is quantum mechanics and is it complete and all this stuff when we've really built and understood quantum computers, because it drives all of the attention towards the remaining problems. We need to answer all of those questions to really understand how to do it properly.
You alluded to this earlier, but I'm curious to hear, what are some of the main barriers towards, as you said, integration and more specifically scalability of number of qubits? And I'm particularly curious about sort of what's setting the upper and lower bounds on that graph up there.
Oh yeah, so the challenges around integration are primarily that it has to ride on top of those other two kind of eras that I defined around coherence first in the 2000s, and then 2-qubit gates with high fidelity and reliability in the 2010s. And integration must maintain those properties, but to do so with larger systems. And that's just hard. It's just it's engineering in the truest classic sense. The primary challenge, I think, is from my point of view, is to develop an approach towards solving those problems that parallelizes things as much as possible and doesn't serialize them, because there's a million micro lessons to be learned and a million micro decisions to be made about how to build a proper machine at that scale, and we just need to learn as fast as we can through proper structuring of the workflow. What's setting the upper and lower bounds here are different assumptions about, in early Moore's law, things, the doubling actually was happening at a faster rate than it is now, or than it has been or it was during the kind of the 30-year kind of heyday. And so we're baking into our assumptions that there's going to be a slowdown in the rate of doubling of qubits on a chip. And the upper and lower bounds on this plot represent kind of aggressive and less aggressive scenarios when that slowdown is going to kick in.
I actually have a question for Louisa about some of the micro decisions that you made actually in the process of writing the book. So the kind of thing that I have in mind is, for example, in comparison, say, with David Kaiser's recent book about how the hippies saved physics. Also a wonderful book, but he tells a very different story with not entirely me, but a lot of different actors. So I was just curious about how you decided. You had mentioned that one of your decision criteria was physicists who write beautifully. I was wondering if you had other criteria for deciding who to include in the story and who to not focus on.
I think that part of it was a literary need to have a story that has a shape, and so picking the people that would make a through line for that story. And I was very lucky while I was doing this independent study at Dartmouth. My professor asked Abner Shimoni, who is a towering figure in the foundations of quantum mechanics and in the story, to come speak. And he really, so this was in the spring of 2000, and he kind of said, one thing he said is, go find John Clauser. People don't talk about him, but the story turns on him. And I was sadly writing this book after Bell just lay down and died at age 62. It was just awful, and so I never got to meet or interview him. But so to pick the living people that I would interview and follow the story, a lot of it was Abner, who had this incredible panoramic view of the field, and he didn't know I was writing. I read a book. I was only a kid doing a paper, but I later looked at those notes and saw that he had mapped out my story for me pretty well, and so I don't know if that answers some of your question.
I've spent my adult life doing research and writing in fields not my own, and that takes a lot of intellectual and emotional heavy lifting to keep going and to speak. And then you read something like Eric Larson's Devil in the White City, where he says, every word I say is from God's honest truth, and you read it, you're like, BS is not. And so you mentioned something about certain paralysis you have about doing the next thing or whatever, and I just wanted to hear you talk a little bit more about these problems and where your thinking and process is at the moment about these things, you know?
Well, I'm certainly in awe of those writers who write, like Eric Larson, and there are a group of these who do write these gripping books you can't put down that are all researched. And I do think it probably helps that, I don't know about Larson in particular, but I do read the acknowledgments, and they're always saying, well, thank you to the 17 students who, read every word of this and that, and so it maybe part of the secret of doing it the right way is to make it more of a team effort, and it is an interesting problem of how to tell these stories. It's so important to tell about science, to tell to bring things out. And yeah, I don't think I think I am the wrong person to ask that question because I haven't solved what's the best way to proceed. But thank you for asking.
Question right here.
Well, talking about problems you have solved, since we're here at a bookstore, I was going to ask a publishing question. So you talk about this was a paper, but you talk about the process of that becoming a book and then pitching it in this in-between space, not fiction, not nonfiction. I find that fascinating.
It was absolutely like a Cinderella magic thing because I spent 4 years running around interviewing people and writing the book, and I was house sitting, and I was working as a movie projectionist, and I was doing these various things while I'd work on the book at night, and then I bound it in this gigantic, shaggy manuscript with my little sketches on the front, and sent it to all the physicists. So there was probably 50 people that I interviewed, and sent a copy to each one saying, you're on page whatever, tell me what I got wrong, and a few of them did also read the whole thing and give feedback. So that was great. And but one of the people that I also sent the book to, my uncle, I come from a family of writers, and which is a huge leg up for publishing, let me tell you. And but my uncle was at the time a New York Times reporter, and I sent it to him, and just to be like, Uncle Jimmy, what do you think? And he passed it along to George Johnson, this wonderful science writer, who actually is among the people that write books that you can't put down, but it's much more accurate than me. And he, there's no reason that George Johnson should have read it. It was a spiral-bound, gigantic manuscript. No reason for him to read it. My uncle, who's kind of a charming guy, was like, my niece, wrote this book on the history of quantum physics. Obviously into the trash that should go. But she's a huge fan of yours. And later, George, who's a very meek, sweet person, not into himself, he was like, that was a non-trivial statement. And he had been thinking about writing a book on the same subject. So he's kind of, how's this kid doing it? And he handed it to him. He liked it, he handed it to his publisher. So there was no agent, there was no, later I got an agent to do they bought it, Knopf bought it, and then I did 4 more years of work. And basically, it was totally unpublishable, but George Johnson says it's worth it. And his editor was like,
we'll trust him, and here you go back and you cut it in half, but you add much more historical detail on each. So it's like, so that was a long project, but that was how it fell out. So sadly, I don't have good advice for.
So one last question. In my opinion, Ray Kurzweil wrote "Singularity is Near," and the really important thing he said is the acceleration of technology is itself accelerating. So my question really for you, Chad, and actually for both, is do you think this might be somewhat pessimistic, your view? That is, it includes having very bright people like yourself working very hard, but it doesn't take the breakthroughs that could come as this becomes more widespread. I mean, there are 6 or 8 companies you listed, and they're going to take, people out of sophomores in high school that are going to do stuff. Do you think it's realistic to think that those dates will come down to get encryption, etc.?
You can, I'm thinking through the question, and I'm trying to think of historical analogies so I can answer with some sort of context. And with Moore's law in particular, there were instances where certain chips would come out from certain, manufacturers that were a little bit ahead of the curve. But once the trend is set, the trend itself is kind of is a self-fulfilling prophecy in some ways through the economic investments that companies make to sustain it, understanding they use it to project where competitors are going to be and therefore where they need to be to compete. So I think that those projections actually take into account an increasing level of investment needed to sustain the harder integration challenges at a greater scale. And so my guess is that significant deviations from this are likely only in the pessimistic direction. That's my guess. And I think that it's not an industry anymore where I think it's really driven by kind of breakthroughs in an office. It's good hard work and in a lab with dozens or hundreds or eventually thousands of engineers that drive it. And that's the kind of stuff that is it's kind of an inch deep and a mile wide, and it's hard to speed that up beyond a certain point. And my guess is that's how it's going to go. And I am no good at predicting the future.